在2025年1月14日，西北大学的研究团队宣布了他们在材料科学领域的一项重大突破，成功开发出历史上首个二维机械互锁材料。这种新材料被称为纳米链甲，其设计灵感源自传统的链甲结构，但采用了现代的二维机械互锁技术。这一创新不仅展示了材料科学的前沿进展，也为未来的防护装备和多种应用提供了新的可能性。研究背景与发展。随着科技不断进步，材料科学的创新也日新月异。传统的防护材料通常较重且不够灵活，而西北大学的研究团队旨在解决这一问题。他们通过精确的设计和工程，创造出一种轻质且强度远超传统材料的新型防护材料。纳米链甲的结构使得它在保持轻量化的同时，具备了卓越的能量吸收能力和强大的保护性能。材料特性与应用。根据研究小组的介绍，这种二维机械互锁材料的特点在于其链甲状的构造。这种结构不仅赋予了材料极高的强度，还允许其在受到冲击时有效分散力量，极大提高了安全性。具体来说，纳米链甲的强度是普通材料的数倍，使其在防弹衣、建筑外墙以及其他需要高强度和轻量化保护的场合具有广泛的应用潜力。轻量化。与传统材料相比，纳米链甲显著降低了重量，这在需要长时间佩戴或使用的装备中尤为重要。能量吸收。该材料在受到冲击时能够有效吸收和分散冲击力，降低对人体或物体的伤害风险。灵活性。纳米链甲的设计使得其在提供保护的同时，仍然保持良好的灵活性，适合多种形态和用途。时间线与未来展望。2025年1月14日，西北大学正式发布新闻，宣布二维机械互锁材料的开发成功，并详细介绍了其结构特性及应用前景。2025年1月17日，这一研究成果引起了广泛关注，被多个科学媒体报道，强调其在防护装备领域的潜在影响。未来，纳米链甲的研究团队计划进一步探索材料的生产成本和大规模应用的可行性。研究人员希望能够将这种材料商业化，使其在军事、建筑和体育等领域得到广泛应用。共同要点与差异。各个报道均一致认为，纳米链甲材料的开发代表了防护技术的一次重大进步。不同来源在关注点上有所不同，一些报道着重强调材料的实际应用场景，例如防弹衣和建筑保护，而其他来源则更关注于其科学原理和设计创新。此外，部分报道对未来研究方向提出了建议，呼吁继续探索材料的生产工艺和经济性，以便于实现大规模应用。结论：西北大学的这一研究成果不仅在学术界引起了广泛关注，也为未来的防护装备设计提供了新的思路。随着进一步的研究和开发，二维机械互锁材料可能会彻底改变我们对防护材料的理解与应用。纳米链甲的轻量化和高强度特性，预示着未来在多个领域的广泛应用，尤其是在需要综合考虑防护性能和使用便捷性的情况下，其潜在价值将愈加显著。
The development of the first two-dimensional 2D mechanically interlocked material by a research team at Northwestern University represents a significant advancement in materials science with practical implications for protective gear and other applications. Here are some counterintuitive aspects of this breakthrough. 1. Lightweight versus strength. While one might intuitively think that stronger materials must be heavier, this new 2D material contradicts that notion. It provides superior protection while being significantly lighter than conventional materials used in armor and protective gear. This could revolutionize how protective equipment is designed, making it easier to wear without sacrificing safety. 2. Flexibility and rigid protection. Typically, protective materials are rigid and can limit movement. However, The interlock design of this new material allows for enhanced flexibility while still maintaining structural integrity under impact. This duality of being both flexible and protective challenges the standard expectation that protective gear must be bulky and stiff. 3. Energy absorption mechanism. The mechanism through which this material disperses energy upon impact is unique. Instead of merely absorbing energy in a straightforward manner, the mechanical interlocking allows the material to redistribute forces over a larger area, which is counter to the traditional view of energy absorption in rigid materials. This could lead to more effective protective gear that is also more comfortable for the wearer. 4. Potential applications beyond traditional armor. While the immediate applications for this material are in defense and protective clothing, its unique properties could lend themselves to other fields such as aerospace, automotive, and architecture. The counterintuitive aspect here is the breadth of application for a material initially designed for specific protective purposes, suggesting that innovations in one area can have far-reaching implications in others. 5. Cost versus performance. There is often a trade-off between the cost of materials and their performance characteristics. While many advanced materials are prohibitively expensive for widespread use, the research is exploring ways to produce this 2D interlocked material at scale and at a reasonable cost. The counterintuitive implication is that cutting-edge materials can potentially become accessible and not just reserved for high-end applications. 6. Historical context of chainmail. The inspiration for the design came from traditional chainmail, which is often viewed as outdated in modern contexts. The use of a historical concept in developing advanced materials highlights how ancient techniques can inform contemporary science, challenging the perception that new technology must always be entirely innovative and disconnected from the past. In summary, the Northwestern University team's development of 2D mechanically interlocked materials not only pushes the boundaries of material science but also presents a variety of counterintuitive insights regarding weight, flexibility, energy management, application diversity, cost-effectiveness, and the relevance of historical materials in modern design. The research led by Northwestern University on the first two-dimensional 2D mechanically interlocked material represents a significant advancement in materials science and engineering, particularly in the context of protective technologies. While many reports focus on the broad implications of this discovery, there are several nuanced aspects that are often overlooked but hold substantial significance for future applications and research directions. 1. Mechanistic insights into material behavior. One aspect that is frequently glossed over is the detailed mechanistic understanding of how this 2D mechanically interlocked structure operates under stress. The material's design mimics traditional chainmail but operates on a nanoscale level, which could lead to entirely new insights into how materials can be engineered to absorb and dissipate energy. This is significant because understanding the fundamental mechanics at play can lead to the design of even more advanced materials in the future. The interlocking nature of the material allows for a unique distribution of force during impact, which is not only beneficial for protective gear but could also inform other fields such as automotive and aerospace engineering. The principles derived from this research could be applied to create lightweight, high-strength composites that perform better under dynamic loads, which is a critical factor in many engineering applications. 2. Broadening the concept of lightweight protection. The emphasis on weight reduction in protective materials is often highlighted, but the implications of this are deeper than mere portability. In military and law enforcement contexts, reducing weight can lead to enhanced mobility and endurance, which are critical for personnel in the field. This material could transform standard issue gear, allowing soldiers and officers to carry additional equipment or remain active for longer durations without fatigue. Moreover, this lightweight characteristic could also open up new markets for protective gear, such as sports and recreational activities where current materials may be too heavy or cumbersome. The potential for widespread adoption across varied applications illustrates how this innovation can reshape standards in protective equipment beyond traditional contexts. 3. Implications for sustainability. While the reports often focus on the performance of the new material, the environmental impact and sustainability of producing such materials are crucial considerations that deserve more attention. If the production processes for these materials can be optimized to reduce waste and energy consumption, they could serve as a model for sustainable innovation in material science. Additionally, lightweight materials often translate to lower energy costs in transportation and application, which aligns with global sustainability goals. If future research can demonstrate that these materials can be produced sustainably, it could lead to a paradigm shift in how protective materials are viewed, not just in terms of performance, but also in their environmental footprint. 4. Potential for customization and scalability. Another critical aspect that could be overlooked is the scalability of producing this new material. The ability to manufacture these interlocked structures at scale will determine their viability in commercial applications. If the research team can establish methods for mass production that maintain the material's unique properties, it could revolutionize industries reliant on protective gear. Moreover, the customizable nature of this material allows for the creation of tailored solutions for specific applications. For instance, varying the interlocking patterns or the dimensions of the nanoscale components could lead to materials optimized for different threats or environments, enhancing the protective capabilities significantly. 5. Future research directions. While the reports highlight the current accomplishments, they often fail to delve into the future research avenues that this discovery opens up. Understanding the limits of this material, such as its performance under extreme temperatures or corrosive environments, is vital for ensuring its applicability in diverse situations. This could lead to further innovations in how materials are engineered for specific conditions, potentially yielding breakthroughs in the field of smart materials that adapt to their environment. Additionally, exploring the integration of these materials with other technologies such as smart sensors or nanotechnology could enhance their functionality. For example, embedding sensors within the protective material could provide real-time feedback on impact and stress, leading to smarter protective gear that can adapt to threats dynamically. 6. Societal and economic impacts. The societal implications of developing such advanced protective materials extend beyond immediate applications. For instance, if this technology leads to safer protective gear for military personnel, it could positively impact public perception and support for defense initiatives. Additionally, advancements in protective technologies could stimulate economic growth by creating new jobs in research, development, and manufacturing sectors associated with these materials. The economic viability of producing and implementing this new material can also influence market dynamics. As demand for lightweight, high-strength materials increases, it could drive competition and innovation within the industry, leading to further advancements and cost reductions that benefit consumers and organizations alike. Conclusion. The development of the first 2D mechanically interlocked material by the Northwestern University research team is a groundbreaking achievement with the potential to transform multiple industries. While many reports focus on the immediate applications and benefits, a deeper examination reveals several critical aspects that are often overlooked. From the mechanistic insights and sustainability implications to the potential for customization and future research directions, the significance of this advancement extends far beyond its current capabilities. As research progresses, it will be important to continue exploring these dimensions to fully realize the potential of this innovative material in various fields. 1. Innovative design and structure. The development of the first two-dimensional 2D mechanically interlocked material termed Nano chainmail marks a significant advancement in material science. Its design, inspired by traditional chainmail, allows for a lightweight yet strong structure that can effectively absorb and distribute impact forces. This innovative design showcases the potential for interlocking materials to enhance mechanical properties while maintaining flexibility, a crucial requirement in applications like protective gear. 2. Enhanced protective capabilities. The material's ability to provide superior protection compared to conventional materials is a critical point of analysis. With strength multiple times that of traditional materials, the nano chainmail can be utilized in various protective applications, such as bulletproof vests and building facades. The enhanced energy absorption characteristics not only improve safety but also open avenues for new applications where lightweight and high-strength materials are essential. 3. Potential applications and market impact. The implications of this new material extend beyond military and defense applications. Its lightweight nature and robust performance could revolutionize industries that require durable materials such as construction, automotive, and sports equipment. The analysis of market trends and potential adoption rates in various sectors can lead to a better understanding of how this material could disrupt existing technologies and practices. For future research directions, while the initial development is promising, further research is needed to address production scalability and cost-effectiveness. Investigating the manufacturing processes, material sourcing, and potential environmental impacts will be crucial for the practical application of the nano chainmail in commercial markets. Evaluating these factors can provide valuable insights into the feasibility of widespread adoption and the material's long-term sustainability. 1. Graphene development. Graphene, a single layer of carbon atoms arranged in a two-dimensional honeycomb lattice, was isolated in 2004 by Andrei Geim and Konstantin Novoselov at the University of Manchester. Its unique properties, including exceptional strength, electrical conductivity, and thermal conductivity, have led to significant interest in its application across various fields including electronics, materials science, and energy storage. The discovery of graphene won the Nobel Prize in Physics in 2010 and has opened avenues for developing lighter, stronger materials similar to the advancements seen with the Northwestern University team's 2D mechanically interlocked materials. 2. Metamaterials. Metamaterials are engineered materials designed to have properties not found in naturally occurring materials, often manipulating electromagnetic waves in novel ways. A significant breakthrough occurred in the early 2000s with the development of negative index metamaterials, which can bend light in ways that traditional materials cannot. Their application ranges from cloaking devices to highly efficient antennas. This innovation parallels the achievements of the Northwestern University team by emphasizing the engineering of materials at the microscopic level to achieve desirable macroscopic properties. 3. Aerogel creation. Aerogels, often referred to as frozen smoke, are ultralight materials derived from gels in which the liquid component is replaced with a gas. First created in the 1930s, they gained attention for their remarkable insulation properties and low density. Recent advancements have led to the development of silica aerogels and polymer-based aerogels that offer enhanced strength and flexibility. Similar to the 2D interlocked materials, aerogels represent a leap in material science, showcasing how innovative structures can lead to drastically improved performance in thermal insulation and impact resistance. Future outlook: predictions for two-dimensional mechanically interlocked materials. The development of the first two-dimensional 2D mechanically interlocked material by a research team at Northwestern University heralds a transformative era for materials science, particularly in protective technology. As this innovation gains momentum, several predictions can be made regarding its future impact and applications. 1. Enhanced protective gear. Within the next decade, we anticipate significant advancements in personal protective equipment (PPE) designed for military and law enforcement applications. The lightweight yet robust nature of the newly developed nano chainmail will likely lead to the production of bulletproof vests that are not only more comfortable but also provide superior protection compared to existing materials. The flexibility and energy absorption capabilities of this 2D material could redefine the design of helmets, body armor, and other safety gear, enabling them to better withstand high-impact forces. 2. Architectural applications. The implications of this breakthrough extend beyond personal gear into the realm of architecture and construction. As urban environments evolve, the need for building materials that offer both protection and energy efficiency will become increasingly critical. Innovations in 2D mechanically interlocked materials could lead to the development of lightweight resilient building facades that can withstand extreme weather conditions. This would be particularly beneficial in disaster-prone areas where conventional materials may fail under stress. 3. Integration with wearable technology. As wearable technology continues to proliferate, integrating 2D mechanically interlocked materials into smart clothing and accessories is likely. The protective qualities of these materials could be combined with sensors and other smart technologies to create garments that not only protect the wearer but also monitor health metrics and environmental conditions. This fusion of protection and technology would cater to athletes, outdoor enthusiasts, and individuals working in hazardous environments. 4. Sustainability and manufacturing innovations. The future will also see a push towards sustainable production methods for these advanced materials. As research progresses, we expect to see breakthroughs in the scalability and cost-effectiveness of manufacturing 2D mechanically interlocked materials. Efforts will likely focus on using eco-friendly materials and processes which could significantly reduce the environmental impact associated with traditional material production. 5. Military and defense innovations. The military sector will be a significant adopter of these materials, particularly in the development of advanced combat suits and vehicles. The combination of lightweight armor with enhanced strength could lead to new designs for tactical gear and armored vehicles, improving mobility without compromising safety. Future military applications may also explore the use of these materials in drone technology, where weight reduction without sacrificing durability is crucial. 6. Customization and smart materials. As research into 2D materials advances, we could witness the rise of customizable protective solutions tailored to specific threats. This might involve the incorporation of adaptive technologies that allow materials to change their properties in response to environmental stimuli such as temperature or impact forces. Such advancements could lead to the development of smart armor that adjusts its protective capabilities based on the situation at hand. 7. Collaboration across disciplines. The interdisciplinary nature of this research will likely foster collaborations between materials scientists, engineers, and designers. As applications for 2D mechanically interlocked materials expand, we expect to see joint ventures that push the boundaries of what is possible in both protective technologies and novel applications in sectors such as automotive, aerospace, and consumer goods. 8. Regulatory and ethical considerations. With the advent of new protective technologies, regulatory frameworks will need to evolve. As these materials are integrated into everyday applications, considerations regarding their safety, efficacy, and environmental impact will be paramount. Policymakers will need to work closely with researchers and industry leaders to establish guidelines that ensure public safety while fostering innovation. Conclusion. The development of the first 2D mechanically interlocked material marks a significant milestone in materials science that promises to reshape the landscape of protective technologies. As research and development continue, the future holds immense potential for this innovative material to enhance safety across various domains, from personal protective gear to architectural applications. By addressing challenges related to sustainability, scalability, and integration with technology, the ongoing evolution of these materials is set to redefine our understanding of protection in the years to come.